Hello, in this section we have another exercise for you to do and check against the provided solution. It's dealing with the t-test. T-test and t-intervals are so important that I provided an example of every possible variation in these slides and one or more of these videos. So by the time you finish this, you definitely should be able to do at least the first 40 homework problems on homework set 4, at least as I have it set up as of this recording. When you're performing inferential statistics procedures, be sure to first check the appropriate conditions and determine the appropriate type of test. Since calculator apps will perform all the work, you don't have to worry about that. Your part is to determine the appropriate test and/or interval, check the conditions for that test or interval, run the appropriate calculator app, enter the appropriate information, figure out which numbers go in which spots, and then see how to take the output of the calculator and use it to state your conclusion in terms of the original problem and interpret your answer. So, most of the hard work, the grunt work, is all done by the calculator, but there's some parts that really require a human being. Those are the parts that you really need to get good at. All right, so here's an example. Let's see if you can do this exercise. An educator is interested in the effect on content knowledge of a professional development workshop given to high school teachers. She gives a test of content knowledge to a sample of teachers who completed the workshop and also gave the same test to a sample of teachers who did not complete the workshop. Summary statistics are given below. Is there enough evidence to conclude that the workshop was effective in increasing content knowledge of teachers? See if you can work this out yourself and come back when you finish. Press pause now. Okay, let's see what we have. We have some summary statistics for each of 2 samples. These are independent samples. So we're testing for a difference in means of 2 independent samples. Assume the distribution of differences in means is approximately normal. Do a population standard deviations are unknown. So we have to use the sample standard deviations. That throws us into t-test category instead of z-test. It is a 2-sample test of 2 independent samples. So it's going to be a 2-sample t-test, which you have on your calculator. We're interested in a higher score for the participating teachers, sample 1. So this is a right-tailed test here. Remember the way your calculator works, it does group 1 minus group 2. So participating teachers are group 1, then a positive difference is better for that means the group 1 teachers did better. So the null hypothesis is that mu of the difference is 0, and the alternative is that mu of the difference is greater than 0. So this makes this a right-tailed test here. So we run our test. This top row is the TI-84 screens. The bottom one is the TI-nspire screens. So for the TI-84 version, you press Stat, Tests, right arrow twice or left arrow once to get to Test. Go down to find it here, number 4, 2-sample t-test. If you see it, you can just type 4. Then from here we go to Statistics because we don't have the actual data. We've got the summary statistics, and we just enter in the stuff from this table. X bar is 75. That's the sample mean for group 1. The corresponding standard deviation is 12, and that's of the sample, of course, and the sample size is 15. And for group 2, the non-participating group, there are 70 of those. The standard deviation is 18, and the sample size is 25. Arrow down, and we're a right-tailed test, so we use the last one, non-pooled, always in my class. And you can either calculate or draw, are your 2 choices here. Either one will get you the p-value that you need. So if we hit calculate, we get this screen here, which down arrow will get you the rest of it. It repeats your statistics down here at the bottom. The things that it gives you at the top are degrees of freedom, which it does figure out correctly, but we honestly don't need to know that. It gives us a test statistic, which we might want to know if we have to compare it to a critical value. But really, the only thing we really need to know there is the p-value of 0.1496. Okay, and we'll come back to that in a minute. And if we can select draw instead, we'll get this picture here, and it shades the right of the difference in the means here the t statistic that goes with that. So the test statistic is 1.05 right here. Probability to the right of that is our p-value of 0.1496. Similarly, we could do the same thing on the TI-nspire. Select menu, statistics, stat tests, one sample, two sample t-test, number 4. Again, you get a dialog box very similar to this where you choose stats, OK, enter in the data just like we did up here, click OK, and it produces an output like this, which is basically the same thing. The main thing we need is that p-value. How do we interpret that? Well, like with any p-value, the p-value is approximately 0.15. Now, there's a little problem here. No value for alpha is given. But with the usual values of either 0.01, 0.05, or 0.1, this p-value is larger than all of those. So with the usual suspects, p is greater than alpha, so we fail to reject the null hypothesis. We probably should have actually decided on a value ahead of time and compare to that rather than do this. But I think if we pick the normal choices, we would not have, we have a p that's bigger than alpha. So a two-sample right-tailed t-test was performed, which produced a p-value of 0.15. At the alpha equals 0.1 level, there is not sufficient evidence provided by this data to conclude that the professional development workshop increased content knowledge. Note that this does not definitely say that the workshop made no difference. It does not prove the null hypothesis, but it does not give enough evidence to definitely support the claim that the workshop did make a difference either. Note that failing to reject the null hypothesis is not the same as proving the null hypothesis is true. We never use hypothesis testing to prove the null hypothesis. In fact, there is often some weak evidence that the alternative hypothesis is true, even when we fail to reject the null hypothesis. In the context of the previous problem, we did record an increase in mean knowledge after the training, or a greater mean of the group that went through the training, which is a little different. But this increase was insufficient to meet our standard alpha level for rejecting the null hypothesis. It might be that the training increased in knowledge, but the evidence collected was insufficient to prove that. It's still fairly likely that the null hypothesis that the training had no effect is true, even though we did not prove the null hypothesis. We also have another problem with this. Even if we had enough evidence to reject the null hypothesis, there's no guarantee that it was the training that made the difference. What we know is would be sufficient evidence to say that the group who went through the training scored higher on that test. It doesn't give a cause and effect relationship necessarily. You could say, well, maybe it's to the training, but maybe they were just a stronger group to begin with. So that's why something like a paired test, where we tested them before the training and then gave them a similar test after the training and looked for an increase in knowledge, that would be a much more conclusive test to see if there was a change.